Hi, my name is Shirsavar, and in this video we're going to talk about the impact of a power supply's phase margin on its step response or its transient response. You may have read that you must have, let's say, a minimum of 45 degrees of phase margin or 50 degrees of phase margin in a power supply. We know from mathematics that when phase margin hits zero, at least theoretically, your system will start to oscillate. So if my phase margin is equal to 0 degrees, we know that mathematically speaking, I'm going to have oscillations like so. Now, does it make sense that your power supply is perfectly stable as long as you've got 1 nano degrees of phase margin and then suddenly starts oscillating as soon as phase margin becomes zero? Well, no, the system gradually becomes more and more goes towards instability as phase margin gets lower and lower and lower. So let's say if I have got a phase margin of around 50 degrees, I expect the step response to be like this. Then if my phase margin gets lower, let's say to around 25 degrees, I expect it to be a little bit more oscillatory. And then at 5 degrees, I expect it to be even more oscillatory with a longer settling time. And eventually, if the phase margin gets to zero, it starts oscillating. And that's why you leave yourself such a big amount of tolerance in terms of phase margin, because it's a measure of your relative stability and it shows how oscillatory the step response is going to be. What we're going to do next is we're going to show you the test setup, and we are using a digital power supply so that we can very quickly change the control coefficients to show you how the step response changes as we lower the phase margin. So here I have WDS. WDS is a power supply design software that we use in our workshops, and it allows you to design analog and digital power supplies very, very quickly and easily. Here I've already pre-programmed the specification of the power stage that I've got, and as you can see here, I can set my crossover frequency and my phase margin. So let's say that we wanted the crossover frequency of 50 degrees. You immediately see that the Bode plot here changes, and you see that theoretically, at least, the simulation is telling me that I've got the 10 kilohertz crossover and 50 degrees of phase margin. I won't go through the rest of the details of how you set everything else up, but if we go to the coefficient section, you see here that I can copy to clipboard. I've also got various tabs for different types of microprocessors that we are supporting at the moment. So if I copy these coefficients, these are floating point coefficients, and I paste them into my Code Composer Studio. These are the old coefficients. We can delete that and we can paste it in. And there we go. What we have now is the new coefficients. Then I can program the microprocessor, and then I can measure the loop. If I wanted to change these, this is now for 50 degrees of phase margin. If I wanted to change these, I could easily go back to WDS, change the specification to 5 degrees of phase margin. This will immediately give me a warning saying that the results are not going to be that great, but I am trying to demonstrate it. So I go back here, I copy to clipboard, and I can now paste it into my code, and now I can reprogram it for 5 degrees of phase margin. So let's show you some measurements. This is one where I have programmed the microprocessor to give me a crossover frequency of around 10 kilohertz and a phase margin of around 50 degrees. And here is the step response for that. Here I'm going from 50% to 100% load step, and in fact I'm taking the load off so you can see the overshoot, and you can clearly see that there's absolutely no oscillations and the power supply is recovering very quickly. Then I reprogrammed it so that I had 20 degrees of phase margin, but I kept the crossover frequency around 10 kilohertz. So that there is no change in crossover frequency. The only thing that has changed is really the phase margin. Now I have 20 degrees, and I expect it to be more oscillatory in nature. And you can see now, compared to the previous one, that now I have got some more oscillations. Let's go back, have a look. This is 50 degrees, 20 degrees. You can see that oscillation is increasing. Then I went one step further and I created a control loop for my power supply that was crossing at 5 degrees, so I beg your pardon, had 5 degrees of phase margin. And here you can see that oscillations pretty much last forever. That is going on continuously, and in fact there is oscillations on the output before I have given it the load step. So let's compare that. This is 5 degrees, 20 degrees, 50 degrees. You can clearly see that as I reduce the phase margin, the power supply starts behaving more oscillatory, and of course this one is completely unacceptable in that it is nearly unstable. If it is in fact, it's unstable. As you can see, as the phase margin gets lower, the behavior of the power supply becomes oscillatory and it ends up being unstable. 45 to 50 degrees of phase margin at the end of the life cycle in an ideal world would be something that I would be comfortable with, and that will allow for the changes in temperature during the operation or capacitors drying up during time, various tolerances and uncertainties, so that you have got enough phase margin that when all of these hand in hand reduce it, you do not get to a point whereby your power supply is unstable.